Hello, guys, and we're back with an episode where we look into someone's code which is related to artificial intelligence. So let's just look for some interesting, um, some interesting code, and we'll look into how it's being done. Yeah. Oh, okay. This guy has an entire project collection, so let's just look into what he's doing. Oh, wow, that's a lot of projects. Um, I'm uh, more attracted towards the Google AI tools, etc. But I have some prior, uh, I have some competence in computer vision, so we just look into that. How about that, huh? Bag of visual words, hybrid images. How about this? Scene recognition. Scene recognition. That sounds interesting, right? Okay, so uh, we'll just go through, say, Gaussian pyramids. That seems like a interesting thing to do. Gaussian pyramids, interesting. Um, well, actually, I intend to do a control click. It opens another tab. Yes, Swift and one and all classifiers. Okay, it opened. Import OS import sys.part, normal stuff. I think I don't need to explain that one. Import CV2. I hope you know what CV2 is, but if you don't, CV2 is a computer vision library for Python, and I think it's there for others as well, including C++ and so on. But majorly, it's used with Python. At least I have used it with Python. Matplotlib used with Python. NumPy. I think it has another variant, but what so on. sklearn is another really famous one. He's importing very few particular things from those. sklearn, he's using it for k-means and mini-batch means and so on. These are all very statistic-based uh, items. Dump load, uh, this is too important and so on. Normalize, scale, SVC is for uh, vectors. Matplotlib, that's the figure. Okay. Neural network. So he's using only uh, sklearn for for his neural network needs, which I intended to understand more of deep learning with TensorFlow, but that's fine. We can just go through his code as well. He's using AdaBoost, which is AdaBoosting is a very interesting technique which was made by um, I'm really sorry I forgot the name, but it was made in 1998, I think. Um, AdaBoost, and essentially what it is it has really bad classifiers, but they're formed in a tree so that a lot of them essentially give you a good classifier at the end. Uh, Arrow boosting with adaptive boosting, meta algorithm by Yoav Fruit and Robert Shapir. Okay, so yeah, they won 2003 Goodell Prize and so on. Anyway, getting back to that code, that's all the imports that we can see which are directly relevant. Pandas, which is again a library for uh, getting all those numbers together. Let's see how he's using them, though that's the real important part, I guess. I With the amount of code that there exists and the number of things that he's imported, I feel that he might have imported more than he needs some places. But let's see what's going on. He's setting up a logging. Okay, so loading training data. He's using uh, he's uh, he's creating variables here, and so info loading label data from so and so. Oh, he's in University of Southampton. How nice. I intend to study in a UK university in 21. I am I'm a graduate from Manipal University, India. Yeah. Anyway, so he has a few scenes. He has 100 samples for bedroom, course, for forest, and so on. He has quite a bit of different scenes. That's nice. Yeah, so total 15 classes, and he's used an interesting sorted method directly to sort out how many samples are there and so on. Then he's used, I'm sorry, um, it goes on and sees stratified shuffle split, which uh, let's just see what that does, right? Stratified, stratified shuffle split. Wow. Scikit-learn. Uh, so it provides train test indices to split data into train and test sets. Oh, okay, okay. So I guess um, here he splits uh, and test side is 0.33 uh, for every one in training. So that means if he has 133 test cases, so he will be splitting them 100 in the training set, and 33 of those are going to be in the test set. So random state, so he's randomizing it based on random state, control the randomness of the training and testing indices produced. Pass an int for reproducible output across multiple function calls. Okay. Yeah, so essentially it's a default is none. So he's not using something which is default. Okay, so anyway, coming back to what was going on. So yeah, essentially he just made two different tables, two different uh, four different variables: x train, x test, y train, y test. Using that, using a for loop to go through all the uh, test and train sets. Dense sift in a Gaussian pyramid. He creates a method called as pyramids, which takes an image, and he also takes step size 5. Okay. Uh, descriptors scaled. That's these are going to be used. Let's just see where for resized and pyramid Gaussian, and so on and so for I in scaled 0 to 4. Uh, CV2 X features 2D. Oh, X features 2D is gonna uh, it's gonna differentiate. Okay, okay. Let's just. How about this? How about this? We'll just use this and we'll Google it. That's the best thing about artificial intelligence. There are lots of things happening usually. So I advise people to look up things as much as they can, including myself, because more or less I have very little uh, understanding of a lot of things that happen. So how about we just see Swift create, because that seems also a logical thing to do. So it's a class reference. Okay. All right. A very familiar page right now. Okay, so the create function, it takes n features int uh, the number of best features to retain. The features are ranked by their score, measured in a SIFT algorithm as the local contrast. Class for okay, so how about we just see? So yeah, essentially, he's going to be ranking the entire thing by. Uh, he's going to retain a few features based on their scores, and those are going to be the n features, the number of best features that you want to preserve. The number of n octave layers, I don't think this person has used n octave layers or anything. Yeah, he has just used the mass minimum things possible. So he's created a sift uh, sift object, which all right. So he's using he okay. So he's created a sift object right here, and he's gonna use it. I'm guessing somewhere now. Oh, see, he's gonna use it here. Okay, so image 8-bit is gonna be the 8-bit image of the entire thing. He's gonna normalize it using the norm min max function. Uh, he's gonna create a 8-bit normalized image of it. Um, if it isn't already in that, otherwise it's going to do the same, nothing much. Kp equals cv to the key points. So he's also creating key points, step sizes, y in range, so and so, x in range, so and so. Kps descending, shift detect and compute. Print np array descends. Okay. All right. So uh, in the end, he's getting a np array of the vstack. He's going to use vstack, and he's going to put the descriptors dot append. So he's going to put the list. He's going to use it to just stack it, and then he's going to make a np array out of it. So all the different it's going to do the same thing for all the different ones. So for I in scale and so and so. So it's going to do for each one. So here's step is 5. Here's so okay. All right. So essentially, what he did here was he used an algorithm in this entire part to uh, get the best features out, as we saw using the sift function, and then he used that to create a, a list saying that these are the best features and these are the ones which are predominant in uh, so many images. And that's what he did for each. Now I think he's going to use this particular function, it's called pyramids, for uh, each particular image, and then get the best like then see how the best features line up with each other to see where that goes. I see. So he's got a flatten um, variable going. Lambda L for L in items for sublist in L for items in sublist. So all right. So uh, all the we've already seen the chain, etc. So he's gonna use that for all the different um, right. So he's going to use patgen, which is another variable that he made for the pyramids of the images which he has made in show where he made the images. Where he made the images? Oh, okay. For image. Oh my lord, what am I doing in life? So we saw the X that he made for. He must have made some X, right? He made X train and XNP, maybe, maybe. Oh, right. So he loaded it as an X. Anyway, so he uses that. Uh, so his patgen function is the one which consists of all the. Uh, it consists of a huge list, NP array, which consists all the different uh, features which are being preserved. So he's mentioned he is going to be looking at the top four features that are being preserved. I feel unit length is lambda x normalized patches. Okay, for patches in x. So he's normalizing the things, and we've already seen what normalize is going to do. His chain. So he's going to create a histogram generator to quantize the entire uh, NP histogram. Okay, so yeah, he's using a histogram quantizer, predict patches, bins quantizer, cluster center dot shape. Okay, so all right, so here he creates he quantizes the entire histogram of the above uh, his, histograms that are provided. Then he is going to use those somewhere here. Oh yeah, see, he made it here. Patchen X train, right? So patches train. So he's gonna feature extract here. So K means mini batch means N cluster 250, random state 219. I have no idea why is he using 219. Why is he using 219? Batch size 50,000. BOBW train. Batches test. Batches train. Um. Alright, so this is gonna be the okay. So he has now made a test BOB. Hmm. K means fit. Okay, so he's put a k means fit on the training data. Mini batch means batch size 50,000. Compute labels true. Inet k means plus plus. Okay. Inet size none max iterate 100 max none no improvement 10 n cluster 250 and init 3 random say 219. I have no idea why 219. SVM train equals list histogen. Patches train k means. So I guess what he's doing here is that he's creating the histogram generator, which we saw earlier, which is here. He's quantizing that, and now he's uh, he's created SVMs that he's going to use to train the actual thing. Alright, so what we've seen this far is that he's taken the images, he has taken the best features of the images, and then he has created a histogram of the images, and now he's creating an SVM of the images. Not yet, he hasn't created them yet. The SVM train is just making a list of the his gens. His gens are just making uh, a they're just making a histogram out of it. Nothing yet, but I feel that that's what he's going to do. But eventually, if at least CLF equals 1 versus rest classifier. Alright, as we see, kernel linear, C equals 4, fit SVM train, Y train, Y predict equals CLF predict, SVM train, accuracy score. So, alright, so Here he just used a 1 versus best classifier. So this is accuracy based on if it's this or any other. Therefore, he's getting a very high accuracy of actually. I don't think he'll be getting that high on accuracy at the end. I hope he does, but yeah, 9.97 is usually a really, really high accuracy for any kind of uh, artificial intelligence system. Y-predict equals CLF.predict SVM test. So right now he's predicted a CLF course, and he has put that in YPred. Predictor accuracy score is of Y test and Y predicted is 0.55 or 56. This shows that there is an ample lot of difference between the actual predicted and the expected. So he's changed the method again, the CLF method, the variable, to be a 1 versus best classifier. Again, in my opinion, that's not the best one, but it's okay, his choice. MLPC classifier, MLP classifier, batch size auto, beta 109, beta 1 is 0.9, beta 2 0.99, 0.999, early stopping, false, so he's going to do the entire thing. Epsilon is 1 to 10 to the minus 8, hidden layers 100, he has 100 hidden layers, learning rate is constant. See, now this is not really a good method, but okay, I think he's going to use a lot of it because we have half the code left. Learning rate is 0.01, but that's going to remain constant throughout the entire thing. So if I could just explain it to you, I hope there will be graphics around this. There's a learning rate, which is how fast it will learn throughout to reach a minimum of wherever you want to reach, the local minimum or the actual global minimum. But the thing is that if he reaches the global minimum, if he's on say a very high slope, and the um, and the alpha or the learning rate is very high and or maybe just appropriate for it, then it'll keep bouncing uh, to and fro from the actual local minimum. And that's why you don't want your learning rate to be that low or that high. What you want is for the learning rate to keep changing accordingly. Like the learning rate consistent, I'm not understanding it, but he has put max iterations of 200. So even if this is not working out, it will stop at a particular given time. Anyway, so there's a momentum factor that he's put of it to be a 0.9. So if it overshoots, it's not going to be the maximum amount of overshooting that's just going to keep on going. So that's fine. N is a no change is fine. N Nestor's momentum equals true. I have no idea what Nestor's momentum means. Let's just how about we just Google it for a second, right? And scikit MLP classifier. Okay, I'm not really scikit-learn guy, but I would really love to learn scikit-learn as well if I get a chance. I guess this is the chance. Haha. So we are looking at learning rate, constant, inverse scaling, adaptive. Adaptive is the one which I would really want. Keeping the learning rate constant to learning rate eine as long as training loss keeps decreasing. See, that's the kind of thing that you need to do. If it's not decreasing and it's increasing, you don't want that learning rate to remain constant, right? Each time two consecutive epochs fail to decrease training loss by at least tall or fail to increase validation score by at least tall if early stop is on, the current learning rate is divided by 5. See, that's a good method. Anyway, we were on a, yeah, uh, nest or was or PROVS. Oh, at least that's somebody's name. Thank God. I thought it's a term which I didn't know, which was really, uh, I thought I was missing out on plain English. Never mind. Uh, um, Nesterov's momentum. Whether to use Nesterov's momentum only used when solver equals SGD and momentum is greater than 0. All right, so it's a momentum type. I'm not exactly sure. I'll search for it and let you know more about it. But for now, let's just see. He's put it as true, and there's a power to it. Okay. Random state, none. Shuffle, none. Oh, shuffle is true, sorry. Solver is an uh, atom solver. There's a total of 0.00001. Validation of friction 0.1. Wilbur is false. So he's just going to give me the output right here. So we're going to predict the CLF directly. And we're going to get the accuracy score by the function directly, and it says 0.2, which is a pretty good score, but of course this person has gone way beyond that. So let's see what else has he done. And CLS accuracy for size and range 50, 800, 100. K means mini batch, K means N cluster size, random state 219. What's with the 219? I'll never know. Batch size 50,000. Oh, I'll check it out what 2019 means. I'm just kidding. K means fit. SVM train list. MPC classifier. So yeah. So this is the one which I want to know. So in this one, batch size is auto. What does auto mean? Okay, I'll figure it out. There's a beta win which says 0.9, beta 2, 0.999, which is the same as before. Early suffix is false. Epsilon is the same. Hidden layer size is 100. Learning rate is constant again. Okay. Learning. I feel that when he changes this to uh, not being constant, as we saw in the scikit-learn before, if he changes it to adaptive, that's when I feel that he'll reach the real potential. But whatever, that's my hunch. See, that's what when you're doing artificial intelligence, I think there's a lot of hunch involved. But yeah, anyway. So he's used the same intravenous momentum as true, random states, verbose, false. All right, so he is using almost the same thing. But what is the difference? I really can't tell what the difference is. It's almost the same. I mean, oh, what the fuck am I doing? It's an it's a different classifier. It's a one rest classifier. One was rest classifier. This is an MLP classifier. For understanding what MLP classifiers are, this is a multi-layer perceptron, and one was the rest classifier is gonna give you a classifying where it is one. So this pretty much tells you what it's at. Machine learning, multi-class or multinomial classification is a problem of classifying instances into one or three or more classes called binary classifications. While many classification algorithms naturally permit the use of two classes, some of the nature are binary algorithms These can, however, be turned into multinomial classifiers as variety of strategies. Multi-class classification should not be confused with multi-label classification, but multi-labels can be okay. All right. So we get the gist of it. So let's get back to this. These are two different kinds of classifiers, and therefore he will probably get very different. Uh, all right. So he gets an accuracy of 0.062, similar to the last one, I feel. Yeah. Oh, my bad. It's exactly the same. All right. So number of cluster optimizations, number of clusters, validation set accuracy. Accuracy is consistent across, almost consistent across the board. It's around, I think, 0.5 to 0.62, where it is a maximum with the number of clusters. So I feel that's where it is at uh, halfway there. It's 30 minutes into it, and I think we'll take a break. We may continue, we may not continue in the session. We might continue it in another session. Uh, anyway, all right, we'll take a little break. We have a few more lines of code to go through. We'll look into it as we uh, in a while. Let's just I think I'll stretch out a little, and you can stretch out a little too. It's 30 minutes into it, so yeah. All right. Have a nice day.